Welcome. In our first lecture topic for the course, we discussed some of the features of a database management system. However, we didn't actually see how these features really work, so the lecture had been pretty much theoretical. What we'd like to do now is to examine commercial relational systems to see how this theory has been put into practice. This will give you the opportunity to actually try some things out and see how they really work. The benefit to this, as I see it, is you'll have a chance to work with the database system early in the course. So you'll have a better appreciation for how these tables that you'll be working with were actually designed. I think this will help you later on when it comes time to talk about database design, data modeling, and you have to create your own set of tables. So let's take a look at some of the ideas in practice of how a relational database system actually works. So what exactly do we hope to accomplish with this lecture? We're going to demonstrate database concepts in practice by using a commercial product. Our discussion of concepts will use Oracle Database as the primary commercial system to illustrate these concepts. However, our discussion will be sufficiently general that the concepts and features are not specific to Oracle Database. They apply to other commercial systems, such as IBM's DB2, Microsoft's SQL Server, or MySQL. The similarity between these commercial products can be attributed to the theoretical foundation upon which these commercial products were built, what is called the relational model. We'll talk about this later in the course. This is E.F. Codd's theory. We'll provide working examples and descriptions of SQL statements, data definition, data control, data manipulation. The SQL we discuss in this lecture is intended to provide you with a feel for the role of SQL in a relational system. We'll examine SQL in great detail in later lectures. We'll also examine how a database management system addresses data integrity through what is called declarative constraints. We'll introduce the syntax, very basic syntax, of the SQL SELECT statement. And we'll explain the role of the system catalog, a metadata repository. Here we're providing a logical view of a relational database management system, again using Oracle Database as our example. Notice that the DBMS sits between the database and these front-end tools. There are a variety of different front-end tools that are available. I list a few of the names that are specific to Oracle: Oracle Forms, SQL+, and Pro-C. The database management system, and here we're referring to it as an RDBMS because it's not simply a database management system, but it is a relational database management system. The RDBMS acts as an interface between application programs or software tools and the database. Applications and software tools such as SQL+ and SQL Developer are used to communicate requests to the database management system to access the data that we've entrusted to that system. The DBMS interprets these requests that have been issued in this language called SQL and then performs the specified operation on the data. So the request could be something like retrieve data from the database, in which case the requested data is read from the database by the DBMS, and the data are then returned to the requesting application or tool. Application programs can be written in many different languages, including C and Java. In such applications, requests to access data use the language of SQL. It's the same language that would be used with an interactive ad hoc query tool. So what is a relational database management system? We say that and RDBMS is based upon the relational model. This is the theoretical foundation put forth by an IBM researcher back around 1970 called the relational model. This model establishes criteria for the logical view or the logical structure of data within the database management system. It also defines the language used to manipulate the structure, and it addresses database integrity. Oracle database as a commercial product is generally quite faithful with respect to the relational model. Remember, the model is theory, and Oracle database is a commercial product implementing that theory. Whenever you're dealing with theory and an implementation of that theory, there are bound to be some differences. The differences are essentially minimal in the case of Oracle database and many of the other commercial products that are out there today. So some aspects of the model may not be supported by the DBMS, but in general, this can be said to hold for all of the commercial products. So why do we see a difference between theory and the application of the theory? Well, software vendors have often chosen to support or implement features that are marketable rather than developing a product that is completely faithful to some theoretical ideal. Thus, we wish to stress that there may be shortcomings in commercial products that are not shortcomings of the theoretical relational model. So in this lecture, we will briefly introduce some aspects of the theory of relational database. The introduction will be quite informal, serving to provide a simple bridge between theory and practice. A more formal and detailed discussion of the relational model will be provided later in the course. In a relational database, data are viewed or seen by users as being stored in a collection of tables. A table consists of columns and rows. These terms that I've highlighted here in blue are informal terms. When we talk about the actual theory of relational database, we'll see more rigorous terminology being used. So we can map this informal relational terminology to traditional data processing terminology by saying a table is logically like a file. When you get data from a file, you read from the file, or you put data in the file, you write to the file. So the I/O operations of reading and writing will not go against the file, but will be targeting a table. So there is the logical relationship. So a row then would be analogous to a record in a file, and a column would be analogous to a field or data item within the record. So each table in a relational database will be given a name when it's created. This is part of that DDL, or data definition language. We create a table by defining its structure, but we also associate a name with that. And we'll see some examples as we go through the process here. Each table generally holds data about one type of real-world object. This is the idea behind what we call a stable, normalized database design. So when we talk about an entity type, each table generally will represent data for exactly one entity type. So the perception of how data are stored addresses what we call a logical view of the data. The relational model does not specify any physical representation. It accounts only for a logical view or logical perception of the data. So informally, this logical view is the table. The mapping of terms that we've introduced here relates back to our earlier discussion of two approaches of data persistence: storing data in operating system files or storing data in a database. Let's take a closer look at this logical structure. Each database table is designed to record data about one kind of thing. The staff table, as shown here, records data about employees or staff at some college. Each row in the table describes some individual staff member or some individual employee. When we design a database table or set of tables, we consider the kinds of things that will be stored in these tables. These tables are analogous to what are called entity types and are similar to the concept of a class in an object-oriented environment. The individual rows would be referred to as entity instances and would be similar to the idea of individual objects instantiated from a type using an object-oriented environment. But unlike a class, an entity type is concerned only with the structure or the data content. It does not address issues of behavior or methods that we would see in an object-oriented world. So it's kind of easy to make the transition from an object-oriented paradigm into a database world, but we have to remember that it's not a clear one-to-one type of correspondence between the items that we're familiar with from one world and those that exist in another. Let's now consider the columns and rows of a table. Each column of a table contains a single data item. We refer to this as an atomic data item, meaning that the system treats it as a whole. Even though we could operate on the individual characters of a string, we treat the string as a whole unit. Likewise, even though we could take a date and kind of dissect that and pull out the month, the day, the year, the date itself would be considered an atomic data type, treated as a whole or a unit. Each column contains values of just one type of data. All of the values in the column would be numeric, or all would be character, or all would be date. It's a homogeneous collection. Each column must be given a unique name within that table. So you cannot have two columns in a table that have the same name. The left to right column order is not important. We describe this or define this left to right order when we create the table, but we're not obligated to always retrieve those columns in that same left to right order. We'll see more about that when we explore SQL data manipulation. The column name, its data type, and the left to right order of the columns is established when we issue the create table statement, when the table is defined to the database management system. So information about that table is preserved in the system catalog. This information is generally not used by an application, but it is extremely important to the operation of the database. Again, this is a form of metadata. Take a look at a row. Each row reflects some individual entity instance in the model world. Each row contains a single atomic entry for each column. Rows are not given names, and the rows are unordered within the table. Obviously, when we render a table on a screen or print out the content of a table, we are imposing an order on what is displayed or printed, but there is no real order imposed on the rows stored within the database. We'll have much more to say about that when we examine the SQL data manipulation to work with the data. So if we consider a table to be similar to an object-oriented class, then a row of a table, again, is similar to an object of that class. The language that we use to work with relational database systems is called SQL, the Structured Query Language. This is used by almost all relational database systems. In fact, there's an ANSI standard that establishes the syntax and the functionality of the language. There are two key characteristics that we want to be aware of when we examine SQL as a language. It's quite different from traditional third-generation programming languages. Two key features of SQL that we want to be aware of is that SQL is quite different from traditional third-generation programming languages. SQL has the property of being non-procedural. What this means is you don't navigate through the database as you would with a hierarchic or network database, but you simply describe the data content. So SQL could be considered kind of a descriptive or declarative language in terms of stating what the result will look like. You don't say how to get it. That's what we mean by non-procedural. In addition, SQL supports set-level processing. So when we provide our description of what the result will look like, all of the rows that satisfy that description or meet that description will be returned. It's not record-at-a-time processing, as we mentioned in our discussion of the hierarchic and network models. It's set-level processing. And this has important implications in terms of data retrieval, but also in terms of performing update and delete operations. You want to be sure that you clearly identify the row or rows that you want to delete. If you're very broad and general in that explanation, you could end up emptying out the entire table. Let's talk a little bit more about SQL. We said that this language is non-procedural. Let's compare that to a procedural language. With a procedural language, constructs such as if then else, do while, do until, and go to deal primarily with how an application's function will be performed. The order in which operations are to be performed is rigidly specified and created by the programmer. In contrast, non-procedural languages are oriented more toward the results of certain operations, leaving the how aspects to some kind of black box, the underlying software environment. The approach of non-procedural languages tends to be more of a hands-off, goals-oriented type of approach. SQL is also supportive of set-level processing. What this means is most of the SQL statements that operate on data do not do so with one row at a time. Instead, they deal with entire groups of rows at once. We had indicated that SQL statements fall into three categories: data definition, data control, and data manipulation. Based on job function, people use different operations when working with a database. Everyone who interacts with a relational database is likely to use the data manipulation operations. These operations are more standardized, meaning that a statement applied to an Oracle database will most likely not require any modification to accomplish the same objective when applied to DB2 or SQL Server. However, there's a greater degree of difference that exists when working with data definition statements and data control statements. Different relational systems have slight variations in terms of features or functions they support, hence data definition could be a bit different. Likewise, the nature of security as implemented in some systems might also take a slightly different twist, so we're apt to see some differences with data control. Let's look at some of these statements and try some of them out. Okay, let's talk about data definition, and then we'll demonstrate some of these commands. A new database object is defined by executing a create statement. There are different statements for each type of object. We can create a table, we can create an index, we can create a view, and so on. So in general, we talk about these as data definition statements because we are defining some kind of object. So here's an example to create a table called pets. There are 3 columns, so the left to right column order by default will be ID num, followed by age, and then followed by name. The data types are also indicated here. ID num will be a short character string consisting of only 2 characters. Age will be a numeric value that allows up to 5 digits. It'll be an integer. And finally, name will be a character string of 20 characters. The information I've just presented to you can be ascertained from reading the code, but the point is that when we execute this code, the system will retain that information as part of its metadata in the system catalog. We have a second table here called computer. And the difference here is that price is numeric, but has 2 numbers describing it. So it's actually a decimal rather than an integer. 2 digits following the decimal point. We can also create indexes as needed, and the indexes can be used for a couple purposes. They can be used to add integrity to the data, for example, enforcing uniqueness if we so desire, but they can also be used to provide potentially efficient access to the data when we run a query. So let's go to the database and try this out. By now, you should have watched the video on getting started with Oracle Live SQL and created your account. I'm currently logged in here, so I'm going to click on Start Coding Now to open up the SQL worksheet. The code that I've been discussing is available to you in a file that I've posted called RDBMS Demonstration SQL. We're going to open that file, and I'm going to copy the create statement for the pets table. Come back to my worksheet, simply paste it here, and I'm pretty much ready to go. So I'll click on the Run button, and the table is created. I get confirmation in the bottom display saying the table was created. But it's kind of like building a house. No one is yet living in there. It's an empty structure. So there's no data currently in the pets table. However, the system remembers all of the information about this table. So I'm going to create a query. Obviously, I won't get any result, but I'll be able to create it because the system will validate it and say, yes, there is a pets table, and so on. So I'm going to ask the system to retrieve from pets all of the columns. This extra code, and there's the query. Select all of the rows, all of the columns from the pets table. And when I run the query, it says no data found. The table is empty. But it didn't say it was an invalid table. If I try to put a name in there of a table that doesn't exist, pets ABC, then I get a different result. I get an error. So it does know that there is a table pets. That's because it's retained its metadata. Let's try this now. I'm going to say let's select ID num and price, 2 of the columns from the table. Well, it tells me it doesn't recognize price. Remember, price is a column in the other table. But if I remove this and select age, again, it comes back, there's no data in the table. But it does not object to age and ID num. It knows that those are column names for this table. In the previous slide, we had shown data definition statements to create a table and also to create indexes. Let's talk a little bit more about indexes right now. Say that a table is a database object that holds an application's data. An index is also a database object, and it is associated with a table. An index could be used for a couple different reasons. It could be used to improve performance of a query or to enforce data integrity. And note here that we're emphasizing it might be used to improve performance. Simply creating an index does not guarantee that the system will choose to use the index. Remember that SQL is a non-procedural language, so the decision to use an index as the way to access the data is not made by users who write SQL, but would be made by a component of the database system called the query optimizer. Because SQL is non-procedural, we actually don't make any statement that says use the index or don't use the index. The decision is left to a software component in the database management system. A table could have no indexes, could have one, could have many indexes. If the table has a primary key, there will likely be an index. Most systems use an index to guarantee the uniqueness requirement of the primary key. So the presence of an index provides an alternative path for the optimizer to consider when processing a query. The alternative ways to get at the data are referred to as access paths, and we'll talk more about this later on. Because the index is associated with a table, when the content of the table changes, the index must be kept up to date. The index is automatically maintained to ensure that it's synchronized with the data in the table. When we create an index, we specify one or more columns over which the index will be created. The values from those columns would be referred to as the key for the index. Think of an index in the back of a textbook. You're doing a search through the index and you're looking for a topic. Let's say you're really excited, so you're reading a database systems textbook and you're doing a search for the term Query Optimizer. You find Query Optimizer as an entry in the index and it says, oh, this is discussed on page 316 through page 324. Query Optimizer is the key. Data definition statements include more than create statements. It's possible that we have an object that we no longer need, so we want to remove it from the database, kind of remove all of the metadata, remove the storage, and so on. This is also a data definition statement. It's called the drop statement. We'll see in a moment that we also have the ability to change or alter characteristics or features of an object. This is another data definition statement. Existing database objects can be removed from the system by executing the drop statement. But remember, we talked about a dependency or an association between a table and an index. So could we remove an index and keep the table? Could we remove a table and keep the index? Let's consider this for a moment. If a table is dropped, the associated indexes are automatically dropped. Obviously, the indexes have no value if the table is gone, because remember, they provide input to where something is located within the table. If the table ceases to exist, what good is the index? An index can be dropped without dropping the table. This is another interesting and important point. Remember, we said that the index can provide an alternative access path, an alternative way for the optimizer to decide how to get at the data. Now, if the index is removed, we can get at the data another way. So it is possible to remove the index, but it might have an impact on the performance of a query later on. Had that query been executed in such a way that the optimizer said, okay, let's use the index, but now the index is gone, it has to look for an alternative route, and this might be a little bit more resource intensive. The alter statement is used to modify an existing database object. There are many different applications for this, but since we've only talked about tables and indexes so far, we cannot say too much about the details of this statement. In the case of altering a table, what we could do is add a new column. For example, suppose we decided that suddenly we need to add one more attribute, one more piece of information about those objects that are represented by the table. We can simply alter the table and add the column. This will change the metadata. How we deal with that in terms of storage is another story, but the point is we have the ability to do this. We could also remove a column from a table. Say, for example, there was a column such as middle name that we decided was no longer really relevant. We only need first name and last name, so we wish to remove that. We can do that with the alter table. We could add or remove an integrity constraint on a table. We can also enable or disable an integrity constraint. Here's an example where we're altering the table computer and adding a new column called processor. Data manipulation statements are used to work with the data in tables. One way of working with them is a data retrieval operation called SELECT. We've talked a bit about this already. We'll discuss this more in a moment as we demonstrate this command. But note here that there are no references made to any index. So I ask you, what characteristic of SQL applies in this situation? If an index is dropped, there are no changes to the DML statement that are required. The same select that we executed when the index exists could be executed once we've removed the index. Again, I ask you, what characteristic of a database applies in this situation? Data manipulation statements include the ability to add a new row to a table. This is accomplished with an insert statement. Remove an existing row or collection of rows from a table. Remember, set level processing is critical here. If we have 5 pets, all with the name of Fido, this delete statement will remove all 5 rows. If we omit the where clause, then we've not narrowed it down. What will happen is we will remove all of the rows. The table will continue to exist, but it will be empty. Update allows us to change the value of one or more columns for existing rows within a table. And again, set level processing is critical here. The where clause will be used to identify which row or rows will be the target of the change. If you omit a where clause, you've suddenly updated all of the rows in the table, and they start to look remarkably similar to one another. Let's carry on with our demonstration. We'll create the computer table as indicated with the instructions in the handout. So let's go ahead and fire this up. And if we examine what's happened here, we'll see the table was created and the index was created. We executed a script, multiple commands. So the two objects have been created, and there's an interconnection here, a relationship between the index and the table. Now I'm going to take some statements that I've included in my file, and I'm going to populate the table by inserting 4 rows. So I'll copy these and clear the display, and then fire these up. So 4 rows get inserted. So now the table has been populated. Now I want to run some queries. So we'll take a look at the first query, and it says, what are the available computers? Select everything from the table, all of the rows, all of the columns. So we'll go back here. Again, clear the display, drop these in, and now we fire this up. And what we get is 4 rows. So all of our data has been placed in the table. Now, how did the system go about doing that? Did it do what's called a table scan? Did it use an index? In this case, we didn't have to tell the system how to access the data. The query optimizer figured out, oh, I'll use the index or I'll do a table scan. It made that decision. But it had a couple choices because the index exists. Try something a little bit more complicated. We'll select a subset of the columns, and we fire that up. Now notice this time we get only 2 of the rows. We have a search condition, or what is called a predicate. In the where clause, we say that the price must be less than 700 in order for the row to qualify to be returned to us. So notice we get 2 rows. The other 2 rows did not pass this test. The predicate evaluated to false. So here we're changing the price to $649.99 where the model is ABC01. This will update exactly 1 row because currently we have only 1 row where the predicate evaluates to true. And sure enough, the feedback message tells us 1 row was updated. Here's the result of the update. ABC01 now has a value of $649.99 for its price. The other rows were not affected. Let's go and try this operation here, but oops, we forgot the where clause. Let's see what happens. So we'll update, setting the price to $649.99, but we don't specify any specific row or rows because we lack the where clause and an associated predicate. So now notice the feedback message says 4 rows were updated. Let's take a look at the result of this. And sure enough, all of the computers have the same price. But let's look at one more point. Let's go back and look at the data definition statement, and we have an index out there. Recall that when we created this table for computer, we created an index called XCompMan for computer manufacturer. Let's suppose we remove that index now. So we're going to say drop index XCompMan, and we run that, and the index is dropped. So now the interesting question comes up. What will happen when I run a query that says, let's select from the table of computer? Will this still work? We fire it up, and we get all 4 rows. In fact, if we had added a condition here that related to the manufacturer, being equal to, say, HP, this was the column over which the index had been created previously, but that index is now gone. We run the query, and we get the result. So the idea is the index is available to the optimizer will consider using it and may use it. If the index is not available, if there is no index, the optimizer can still figure out a way to get at the data. In this video, we began our discussion of relational database. We talked a bit about the relational model and mentioned that it establishes criteria for the logical structure of data, a language or set of operators to manipulate that structure, and it also addresses data integrity. We described the logical structure and talked a bit about the manipulative language of SQL. Although SQL was not part of the relational theory, it is a de facto standard relational database query language. In our next video, we'll conclude our presentation on Introduction to an RDBMS, and we'll discuss database integrity. So I'll see you soon.